because other people are not coming. Okay, so let's just take a quick review of what we had done yesterday. Okay.
Okay.
Yeah. So what can we say as a review? So yesterday we started with discussing useful sets from an analytic point of view, right? Useful sets, right? And of course, our sets are ordered sets. Okay. We would want ordered sets. And on top of that, we discussed that we would want our sets to be dense, right? In the sense that between any two elements, there should be an element, dense with respect to that order. Because naturally, the sets that we are trying to study in analysis would be like, would serve as time, you know, or parameterizing a certain kind of motion. So we don't want gaps. So definitely we want denseness. Okay. And the second thing that we also wanted is every uh, bounded set, every bounded set should, you know, have a least upper bound. Yeah. So we also discussed this, right? We saw that this is very important because we would want our sets to have a maximum if they are bounded. We would want them to have a maximum and a minimum, but sometimes that is not possible. So the next best thing is that if you take the suppose you have a bounded set, the next best thing is that if you take the collection of all upper bounds, then that collection of all upper bounds should have a minimum. Is that right? Right? That's the next
Mhm.
best thing we would want. So definitely Q has this property, but Q doesn't have this, right? So we have to extend Q. So I'm not writing everything because this is kind of a review. So we have to extend Q to a bigger set, okay? And we don't know if such a set, we don't know if a set exists, but we have been told that it does. And I think some people even suggested ways, to how to show that such a thing actually exists. But let's assume that it does exist. Okay, so there is in fact a bigger set which actually we call the real numbers. Okay, which has the property that every bounded set has a least upper bound. Okay, and this R is the least such thing. Just what it does is it takes subsets of Q and it adds the supremums of all the bounded subsets, and you get this new thing R. We have been told that such a thing exists. Okay, and the other thing that followed from the consequence of this is that Q is dense in R. Now, mind you, I have not defined this statement Q is dense in R, but we understand that if X and Y are in R, X less than Y is in R, then there exists a Z in Q such that X is less than Z is less than Y. Okay, so between any two real numbers, there is a rational number. These are the things that we showed the previous day. So certainly we realize the importance of having least upper bounds in foresight, right? So we saw that bounded sets should have a least upper bound because that's the next best thing of maximum and minimum. Okay. However, you can also look back. I mean, or probably you could also look, for example, what I
Another.
mean is that algebraically, what I mean is that you would want these kind of equations to have solutions, right? You would want x square equal to 2 to have solution. You would want x cube equal to 2 to have solutions. Okay. In fact, these are slightly algebraic requirements, but you would want these things. You would if r is a real if r is a number, not real actually, because the requirement has to be satisfied for rationals, and for that you need real numbers. If r is a rational number, then you would want, you won't want to have numbers x such that x to the power n is equal to r. What I'm saying is you would want nth roots to also exist. You would want more arithmetic. Okay, so for that, these reasons also supremums are important. Okay, so I will ask you to show that given a rational number, prove that there is a real number x such that x to the power n equals to r. So such a real number exists. How to show that, you'll have to prove. Okay, so you will realize that this x would turn out to be the supremum, right? So you would take, naturally, right, you would take all rational numbers q such that, such that q to the power n is less than equal to r, right? And you would take the supremum of this set, and deep down inside we know that this is what the x's, right? I mean, the supremum is x to the power n. Now you have to just prove it. The proof will be very similar to yesterday what we did, right? X square less than 2, q square less than 2, and so on. So lot of good things, you know, lot of how do I call it? A lot of key points, key solutions, maxima, minima, and a lot of stuff such turns out to be supremum of certain things. Okay, so yeah, so really that's the thing, and in some sense, it also fills the gaps between the rationals, because in this naive sense of gapness, rationals have no gap, right? But in the supremum sense of things, they have gaps. So to fill that up, also you could say that real numbers are important. So real numbers, now this R is a very good set for us to do analysis on. Okay, every bounded set has a supremum. That's a good thing. Okay, so this was just a little bit of a review from what we have done yesterday. Okay, but now let us isolate and abstract. So what do I mean? So let's isolate and abstract out the supremum operation. It's not really an operation, it's kind of a function, right? What do I mean? We are seeing that a certain quantity is there attached to bounded sets, which is very important. That's the supremum. So what we want to do now is we want to study its properties, basically. Okay, we want to study its properties because we are realizing that this will come up in many places. Okay, so let's study its properties. Okay, so as of now, we all know the definition. It is a least upper bound. We will see if we can get a better definition. So what are the properties of supremum? So first of all, let's think of it like this. So if you take the power set of R, which means all subsets of R, right? So A, every set A is mapped to sup A, right? So in that sense, it's a function. It's a function from the power set to this. To R, I mean, sometimes you might have to take the infinite number, because certain sets will not have a supremum. It will be infinite, okay? Or, so before that, let me ask the question. So before we try to study properties of supremum and supremum of certain sets and how we can calculate them and so on, let's see. Before that, let's ask a logical question. So really, this is a logical issue here. What should be the supremum of the empty set? So phi, we all understand phi is the empty set. Okay, we'll assume that it exists. Yeah.
Minus infinity.
Okay, so Noel is saying minus infinity. Okay.
Ah,
So anybody would want to explain it? So I'm not asking you to explain because you have given the answer, so you must have thought something. Anybody wants to explain this? Suddenly, why is it minus infinity? You can you increase your voice, Subham? I want you to explain it.
Hello.
Yes. Yeah. Go on.
Every element in R is basically an upper bound of this set. So in that sense, we can think of minus infinity as a supremum of phi.
Yes.
More
Right.
specifically, we can define it.
That is right. Yeah. So what he's saying is a finer point. Okay. That's basically because no such real number exists. It's less than every real number, and so we define it to be a new thing, which is minus infinity. That's a good. Yeah. Good point. Yeah. Good point. So every real number is an upper bound, right? Because if you take x, and x is bigger than everything in the set because nothing is there in the set. So by it's true, like in a trivial sense. Yeah. So but to prove that it is true, you have to go by contradiction. Assume that it is not true. So there is a real number such that there is a real number x in phi such that it is bigger than that, but then there is no such thing. So that statement is false. So the negation is false. So the statement will be true. So there we are really using that, false of false is true. I'm saying that double negation is always true. So yeah, this is what we are using. This is something that which is obvious, but this has to be put as an axiom in the ordinary maths that we do. But there are branches of maths where this is not true. Okay, where truth is not Boolean in nature, but all that is different. That basically goes into constructive mathematics, where you cannot use proofs by contradiction, because whenever you're using a proof by contradiction, you're always using the fact that not of not means true. Okay, but that's a logical issue. Let's not go much more there. Okay, so we understand that. And now there are certain other properties that are very expected properties. And what we will do is we will just like do one or two in the class, and the rest I will ask you to do on your own. Okay, that's mostly just a matter of writing proofs. But let's just do at least one of them. So as you would expect, okay, but there are sometimes certain exceptions. So I will ask you them. Okay, and then we will move on to problem solving aspect. Right now we are just doing the proof writing aspect of it. So this is very expected statement, right? But let's prove it. So here again I would just say that A and B are bounded sets. Even if it's not bounded, it is still true. Probably is it okay? That can be checked. Probably maybe it's not true. Okay, yeah, that may not be true, so I'm taking that back. I'll give you that for homework. So right now A and B are bounded. Yeah, so can anybody just try? This will be the last thing that we'll prove, then we'll move on to problem solving aspect. Let's see.
Yeah, you can take the supremum since A is bounded. So supremum of A exists by completeness property of R.
Yes, yeah, it exists. Yes, because we have written them here,
So
so they exist. That's fine. Okay, go on.
so let it be let the supremum of A be capital M and that of B be small m. So we will
But we are already have written it to be sup A. But okay, if you want to give it a new name, you can give it. Not a problem. Okay.
oh, acha,
Yeah, you understand. Like I've
okay.
already given it a name. But yeah, go on.
Then we can show that it is an upper bound of the set A plus B, sum of A and B.
Okay,
And
can you say the details there? So he wants to
because
say that m plus m. Yeah, yeah.
for all x belongs to A, x is less than equal to small m, and for all y belongs to B, y is less than equal to capital M. So x plus y is less than equal to capital M plus small m. So it is an upper bound, and we have to show that it is a least upper bound.
Yes.
So we will proceed by contradiction.
Yeah.
Let us.
Yes. Go on. You can say so. Okay. So assume x plus y is not the least upper bound, or
No, not x plus y. Capital M plus.
oh, I'm sorry. Yes. Yeah. Small m plus capital M is not the least upper bound. Okay.
Hello.
Yeah. So what do we do then? So if m plus m is not the
Hello.
least upper bound. Hello. Yeah, Noel, can you hear me?
Yes, sir, I can.
Oh, so I think so. Suvam is not able to hear us. No, mind. I'll say from here. So
So
basically,
I had another thing from here. I mean,
yeah.
my own.
Please say. Yeah.
So we consider the set A plus B, right? Which is basically adding all the elements of A and B, right?
Yeah.
So we can say that the supremum of A plus B will be uh, yeah, okay, 1 minute. Let me think how to frame it. So supreme A plus B, the set A plus B, in that we can say that either supremum of A or supremum of B is bigger, right, than the other, right?
Okay, so they can be equal also. I mean,
Yeah, they can be equal, but the equal case is easy to show. I mean, that is
will it be easy to show? I don't know. Two very
so
different
then,
sets can have the same supremum.
yeah, that can happen, but then this statement will be like this, right? Supremum of A, then we can say that supremum of A equal to supremum of B. Then it is basically equal to supremum of A plus B equal to 2 times supremum of A.
But what? But if you have to prove that, yeah.
But supremum of A plus B is basically the
Yeah, it is. It is like the maximum, but it is not the maximum.
yeah.
Yeah, it is like the maximum though. Yes. So again, this is a statement which is very obvious, but it's not like, it's a little interesting to prove it. Okay. Yeah. Okay, so I'll just say the proof, okay, and I'll give you very similar questions to work out. Okay. So see, basically it is an upper bound is clear, right? Because as the other person has said, right? So it's an upper bound.
Yeah.
So let's just take something. We don't even have to go by contradiction, in fact. Okay. What I'm saying is that take a number which is less than m plus m. Okay. Which means that take this. Okay. Take this number, small m plus capital M minus epsilon. I will show, we want to show, right, that this is not an upper bound. Is that right? M plus M minus epsilon is not an upper bound. This is the most logical thing to try because you want to show it's a least upper bound. So you just take your claimed least upper bound, which you think is the correct answer, and you take something smaller than that. This is an arbitrary quantity which is smaller than that, and show that this is not an upper bound. So how do you show that this is not an upper bound? So see, for this you will have to use that sup A is the least upper bound, right? And sup B is the least upper bound for B. Is that right? Okay. So is not an upper bound.
Hello.
Yeah.
Am I audible?
Yes. Yes. I think you got disconnected. Yeah. So I'm just completing the proof. Yeah. So okay. So I'll just say the proof and then I'll just ask you to see if there are any mistakes. Okay. Let's see. I'll leave something there. Okay. So I will show that this is not an upper bound. So this reminds us of using this. The sup A is the least one, right? So M minus any epsilon you take, this will be less than some x, this will be less than some A in A. Is that right? Okay. And similarly, if you take anything less than capital M, anything less than capital M, then that would be less than some B in B. Is that right? Okay. So here we would, once you add them and you choose your epsilons, epsilon 1, epsilon 2 wisely, because that's up to you to choose. You choose them to be both epsilon by 2, right? Because eventually that's what you want. So you choose them to be epsilon by 2 and you get this minus epsilon is less than A plus B. Okay. And of course, A plus B is in A plus B, right? So I have basically taken something smaller and I've produced, I've shown that it is not, that's not an upper bound. Basically something else is bigger. So I do not have to use contradiction. Okay, as much as possible, proofs, if you can write them without contradiction, then it means that they are constructive in nature. You're actually showing something, you're actually showing that something exists that makes it happen. Okay, so is this proof okay? Yeah. So I will give you people some other questions to try like this, and you can write and send me the proofs. Okay, that will be better. But this is the first example, so I just gave it there. All right. All right. Let's move on. Let's see where we can go from here. Okay. So this was about properties of supremum. All right. Now, as people know, I guess, there is a dual concept to the supremum, and that is the infimum. Yeah. Can anyone please define it? Infimum of a bounded set, let's say. Okay. So this is basically the greatest lower bound. Is that right? It is the greatest lower bound. Now see, every bounded subset must have a supremum. This is what we demand. Or every subset that is bounded from above must have a supremum. Okay. But on the other hand, every subset that is bounded from below, we would want that to have an infimum also. That's also just the equally important requirement, right? So, okay, the definition of infimum is clear, but also infimum is equally important. So infimum is equally important as supremum. No doubt about that. So now what should we do? We have the real numbers, right? And real numbers has a supremum property. That's how we have defined the real numbers, right? It's a field that contains Q which has a supremum property. Every bounded set has a supremum. Now, what do we do about the infimum property? Should we now extend R further so that it has the infimum property also? Or should we put another axiom in the R that it should have the infimum property also? Or
It basically follows from the supremum property.
it follows from the supremum property? Nice. Nice. Yes. So that is basically what I was going to get at. Yeah. So in certain cases, they just say that it has the infimum property, but it in fact just follows from the supremum property. R has the infimum property. So let me just abstract this out, or let's not abstract it out now. Let's just see how we can prove this. Yeah. So again, since Subham has said this, can you try to show us why this happens?
Yeah,
Or you can even
let
give an
us take
idea. Yeah.
a subset, say A of R, which is bounded below.
Okay. A of R is
Which is,
bounded below.
then we have a lower bound of A in R, say U.
Okay. U is
So
a
U is,
lower bound of A in R. Okay.
so U is less than equal to X for all X belongs to A.
Okay. U is less than equal to X for all X belongs to A.
Now
Okay.
let us define a new subset by taking the collection of all lower bounds of A.
So let me call that L. Okay.
L.
So this has Y such that Y is less than X for all X in A. So this is a collection of all lower bounds. Very nice.
Now
Okay.
this is bounded above by any element of A. So by supremum property, this has a supremum, and we will basically
Okay.
try to show that supremum is basically the infimum of A.
Okay. So this is his claim. This is the claim.
And yeah,
Okay. Nice. So again, I would just want you people to work it out. Okay, and write a proof. Okay, and convince yourself that it actually. Again, we will have to use the same kind of arguments. Yeah, I don't want to do it in the class right now. It's simple. But Noel, can you give an intuition behind why this is true? Does it look intuitively true? Yeah. So let me see. Let me.
It
Yeah.
does, but yeah, me, yeah, it does look it.
It does look intuitively true, right? So
Yeah, yeah.
you have a set which is bounded. You take all its lower bounds. Because it's bounded below, it has a lower bound. So this point which he has mentioned in the beginning is probably very important. So we should not skip this point. And he has mentioned it rightfully that there is a u which is there. It has a lower bound. Okay. Otherwise, if it's empty, then it will be like infinite or what not exist. So it has a low set of lower bounds. Then you take the biggest of these lower bounds, and the biggest of these lower bounds exists. That is because of the supremum property. And now you have to show that this
Because I
is
think
the
it is intuitively true because we can define the real number set via infimum also and get to the supremum thing.
that will
So
show that they are equivalent. Yeah, I think
yeah,
that is.
so
I think your point makes sense. Hmm. No, but I was saying that why your proof technique is intuitively correct. Okay, what you're saying is that why the theorem is intuitively correct. So theorem is intuitively correct because I mean, if you take minus r, that is also r, right? So if you take the negative
yeah.
of r, then it's also r. So that's the basically the easiest way. I'm saying one way to say that. Okay. So here really we are using the arithmetic, right? We are using the arithmetic property of R to say that, you know, if every set has supremum, then it must have infimum also. So again, I want you people to write out a proof, a simpler proof than what Subham has given us using the arithmetic of R. Sometimes that extra structure that the set has can give you an easier proof actually. Okay, so I want you people to do that. I will write that formally as a question, properly stated.